Welcome everybody. Hopefully those online can hear me okay. It's fantastic to have a really good turnout for this meeting, technical talk. It's been a little while since we've managed to hold an event, and it's really good to see some new faces or returning faces tonight that haven't been for a while. As I said, probably to a few people, the usual venue we had a few issues with, so we thought we'd try somewhere new and fresh, and this seems to be popular. So yeah, I'll get some feedback from people, and you know, we could continue to use this venue. Again, thanks for people online. I'm just going to go through a few housekeeping slides first before we get started, and then I'll hand over to the talk. So I'll start by saying ASEG acknowledges the traditional owners of the land on which we meet today, and all of the lands that we undertake our work on across Australia. We recognise their continuing connection to these lands, water and culture, and pay our respects to their elders. I'd like to thank our ASEG corporate members for their ongoing support. This list hasn't changed much in the last many years, so thanks to all those that support us. I'd also like to thank the grant sponsors, which I always put up a little bit begrudgingly because there's a whole bunch of sponsors for WA and SANT, but not too many for Queensland, so we're always interested in getting some more sponsors for our branch. And if we get this number of people coming to our talks, then maybe it's a bit more of an incentive there for people to get involved. So just some Zoom housekeeping. Again, thank you very much to there's 27 people online, which is again a great turnout. And if you have, please yeah, keep your lines muted. I don't know if you can unmute them anyway, but if you have any questions, please put that in the Q&A box, and we'll make sure we try and get to those later on. So hopefully most people that are here know the benefits of ASEG membership, and most people should have seen, I think, an early bird renewal for next year. So please make sure you get on and renew for next year. It will save yourself a bit of money. Certainly we've had a little bit of a decline in membership over the last few years, but you know, I think there's a lot of optimism and excitement around the industry, and I think this talk tonight kind of shows some of the innovation that's going on, and some of the exciting things that hopefully are going to really help us for exploration in the future. So yeah, please do get in there early, renew your membership, and get involved. And finally, keep in touch. So obviously, hopefully people would have seen the email adverts for this talk. We do try to get those on LinkedIn and the other social networks. But if people find they're not getting enough information, then please get in touch, let us know. And yeah, we can improve how we communicate, but I think we're certainly getting better at that. And yeah, it's good to see a lot of people here tonight. Okay, so that's all I've got to go through for now. I'll open up the main event. So I'd like to welcome Dr. Gerrit Olivier from Fleet Space Technologies to come and give a talk tonight. I've been wanting to try and get these guys to come and talk for a while, so it's great to have him here. And I'm going to let Gerrit introduce himself, and yeah, we'll get going. Yeah, if there's any issues with the online content, let us know. We'll try and sort it out. Thank you.
Thanks James, and thanks everyone for attending, and thanks for ASEG for organising this talk. The talk today is going to be a little bit all over the place. I don't just mean Earth, Moon, and Mars. I mean also in content. It's going to be a little bit about fleets, a little bit about our motivation for entering the mineral exploration industry, and also the motivation for building our own nodes, and then also our ambitions to use our devices on other planets and on the moon. Yeah, so as I mentioned, I'm Gerrit Olivier I'm from Fleet, and I'm Director of Planetary Geophysics. I did my PhD in geophysics and seismology in France in 2015, and I've been working in the mining industry for 11 years now. So just a little bit about Fleet, first and foremost. So we are a company based in Adelaide with some pretty audacious goals. So we've launched 7 satellites into orbit so far. We launched Australia's first commercial satellite for commercial nanosatellites in 2018. And we hope to expand our satellite constellation to more than 200 satellites in the near future. And we also hope to deploy geophysical devices on the Moon and Mars. I mentioned we've launched quite a few satellites, 7 thus far, and 2 more scheduled early this year. We build our own satellites, and a few things make our satellites unique. Firstly, we do digital beamforming on our satellites, which is the first for nanosatellites. That increases throughput and still keeps the satellite quite small. We also 3D print a lot of the components of our satellites. So, for instance, attach antennas, we 3D print, and that's all in manufacturing costs down. So, in a lot of ways, our satellites were. So, in a lot of ways, our satellites were advanced nanosatellites, and obviously, there are lots of people in the satellite industry, but there were advanced technology looking for an application. And a few years ago, the companies decided to, instead of building a satellite constellation and waiting for applications to, or for waiting for people to connect to that, we thought we should rather go and fully vertically integrate ourselves in certain applications that need satellites. And we investigated a lot of industries that need remote real-time data. And one that stood out in particular was mineral exploration. So earlier this year, we launched a product called Exosphere, which is a real-time seismic imaging method that uses geodes or satellite-enabled geophones or nodes, and creates a real-time image of the subsurface. I'll talk a little bit about our motivation behind this, and then also basically how the method works. The motivation behind it was pretty obvious. We all know, and I'm preaching to the choir here, that we need to find a lot more mineral deposits, and especially critical mineral deposits, to meet our ambitious energy transition needs. So this is clearly an area where we have to innovate, and we have to use a lot of new methods to find new deposits. And to kind of also motivate why we investigated or why we did research in this field is we have to look to the past to think how we made discoveries in the last few decades. And 2 of the methods that worked really well has been soil sampling and airborne geophysics. And one of the reasons why that's been really successful.
Sorry, I just heard that they can't see the presentation online.
Okay.
So I'm going to just try again.
Okay.
Just do that again. You see that now? Okay, let's try again.
Yeah, hopefully you can see that now. If anyone online can't see the screen, then please let us know. Yeah, so in the last few decades, a couple of methods that have worked really well to find new deposits, or at least to identify drill targets, in soil sampling, which kind of shows deposits that are obscured by, say, thin regolith, so we can still see the geochemical signatures of the deposits, or airborne geophysics. So you see a lot of gravitational discoveries due to gravity surveys, so like for instance Olympic Dam or Cartagena. And these methods are really effective because you can scan large areas really quickly. So for airborne geophysical methods, you can cover thousands of square kilometers in a go and cover a large area quickly. The limitation, of course, with potential field is the non-unique nature of the potential field that we measure. So if we measure a gravity anomaly, we're not sure what the cause of that is. And sorry for some of my very simple sketches here. But what we can see is it's hard to distinguish what is the cause of a certain geophysical anomaly that we're seeing. And so, for instance, we can see something like a paleotopography high can cause the same gravity response as a dense body in the basement. Even if we're not dealing with cover, we still have the non-unique problem with potential fields, and that we don't know the size and the shape of the body that's causing the gravity anomaly. So one of the methods, or one of the, I suppose, tools that have a lot more favorable depth sensitivity response is, of course, seismic methods. And seismic methods, of course, have done an incredible job in the oil and gas industry, and especially offshore oil and gas industry, to find new deposits. So active seismics are used for almost all oil and gas exploration projects. In the mining industry, we've kind of used one of two methods. We use HDSR, which is a passive seismic method that measures the peak and horizontal to vertical spectral ratios. And from that, you can typically get the depth of some interfaces. So, for instance, getting the depth of glacial till or regolith in WA, for instance, HDSR works really well. There are limitations due to the depth penetration and the resolution. It's a point measurement, so there's some resolution limitations, but nevertheless, it's still a very effective or very useful method in certain settings. On the other end of the cost versus capability scale, we have active seismic, and companies like iSeis obviously are doing a really good job in that space. And from that, we can create very detailed 3D models of the subsurface down to quite significant depth. The problem, of course, is the cost, and this isn't just the cost per square kilometer, but it's also permitting, line clearing, and all the kind of logistics that go along with 3D active seismic surveys. And the interesting thing about this is that in academia, there is actually a big field smack bang in the middle of these two. That's a combination of active and passive seismic methods. So, for instance, in areas that are seismically active, travel time tomography or receiver function approach can be used. And another method that really fills the largest part of this space nowadays is a method called ambient noise tomography. Yeah, so ambient noise tomography we can think about as a method that recycles the Earth's hum. So basically, we listen to faint background vibrations that are from different sources. At low frequencies, it's typically the interaction of the ocean with the coast. So that creates seismic waves or surface waves that we can record everywhere on Earth. And at higher frequencies, human activity like traffic, railways, near mining sites, crushers, mills, these all generate seismic noise. And so in the early 2000s, people showed pretty comprehensively that you can use the Earth background noise to image the subsurface. So the image on the right here shows one of the first applications in 2004, imaging parts of the San Andreas fault with the interaction of the ocean and the coast. So this kind of led to a boom and boomless seismology, where you could use passive seismic sensors and noise to image the subsurface, and you didn't need an active source or earthquakes to do that. The method obviously has limitations, and I'll spend quite a bit of the time during this talk discussing the limitations and applications of the method. There's some really good background reading or an introductory reading about how we extract information from noise. So you can read either of these two papers. The one on the right, the figure is really the kind of the crux of what we're doing. If we have two receivers that are recording noise, and if we cross-correlate and stack and do some other pre-processing steps, we can retrieve the same signal as if you replace one of the receivers with a source. that's why it's kind of referred to in some circles as the virtual source method. Now, there are caveats here, because obviously we have some active seismic folks in the crowd here. So body waves are really hard to recover. Body wave reflections are even harder to recover, but surface waves are relatively easy to recover. And that's just because of their relative strength in the ambient noise field, and also because of their relatively unique late arrival time compared to body waves. So the method is predominantly being used on really large scales, and I call it like regional or tectonic scales. Here are two examples, one showing low velocity zones below the Japanese volcanic arc, below all the volcanoes, you see these low velocity zones. And on the right-hand image, we see the difference between the tectonically deformed western part of the US and the stable mid-continent region. You also see like a low velocity zone similar to the Japanese case under Yellowstone volcano. So there was a kind of and of course the WA array that's due to launch this year, or as a already launched perhaps, where the entire Western Australia will be covered with passive seismic stations with I think 40 kilometers spacing. And again, the idea here is to use ambient noise and earthquakes to image especially the lithosphere chromosphere boundary. So there was a particular, so there's been kind of some reasons why the method has gained popularity in recent years. And a lot of it has to do with the advent of nodal seismic stations. So for instance, the smart solars or renewable quantums or fairfield nodals, for instance, these stations have made it really easy to collect passive seismic data as well. Obviously, it had a huge impact on how active seismic surveys have been done, but it also allowed other seismologists to collect passive seismic data for relatively low cost and for relatively easy cost. So the Long Beach experiment, which was an active seismic deployment where passive seismic data was recorded alongside it, was one of the first applications on an industrial scale that showed that you can use the hustle and bustle from LA to image parts of the San Andreas Fault, just purely from the noise in the city itself. So yeah, so over the last few years, there have been a lot of applications of the method on smaller scales, but one of the drawbacks of the method is it takes quite a long time relative to the value of the output that it provides. So you get a 3D model of the subsurface and of the seismic velocities. It can be really useful, but if you want to scan large areas really quickly, then we can't really wait months from data acquisition to getting a 3D model. A lot of the bottleneck was around the data acquisition, harvesting, and processing. So we would record data on hundreds of devices for months, potentially, which would be terabytes of data, which would then need to be shipped all over the world. Data would need to be harvested and then data processed. And what we found, especially in some of the early mineral exploration applications, were that by the time we provide a 3D model, the project might have gone stale, focus might have been shifted elsewhere, or yeah, it was just not that valuable or useful information anymore. Yeah, so nevertheless, there have been some really compelling case studies for using the method in mineral exploration. So here are two examples. One on the left gained quite a lot of traction recently. This was a study for core lithium where we imaged the pegmatite dike, a known existing dike, and the image on the right shows a case study of imaging under hundreds of meters of sedimentary cover. So there's been quite a lot of applications and a lot of questions about how the method works and where can it be used. So for the next few slides, I'm going to go through basic principles of how the method works, and basically also discuss with some two examples what we can and cannot image with the method, and basically what are the typical expectations that we should have around our depth and resolution. So at the moment, the method is kind of settling in the mineral exploration industry and finding in the areas where it can be useful. And I think if we have a discussion about the limitations, then that will go a long way towards that as well. Yeah, so the basic concept about correlations and noise is that if we have two stations like these two numbered here, and we record noise coming from a specific location or an impulsive event from a certain location, if we cross-correlate the two signals that we record, then we'll get a peak at the lag time which corresponds to the arrival time difference between the two stations, of course. So in this case, it's around about 1 second. So you can pretty quickly see that if this source was exactly aligned between station 14 and 41 with the station pair, and we cross-correlated, then the arrival time would be exactly at the travel time between the two stations. So you get the same wave speed information as if you did if you replaced 14 with the source. So it's pretty incredible, but if you instead have noise coming from everywhere, so if you have noise coming from all directions, and you cross-correlate enough of that and extract enough of that, what you see is that all the noise locations in red destructively interfere. So these are all the arrivals near the middle, they all destructively interfere. And only the ones in these green dashed lines, which corresponds to the stationary phase locations, they're the only ones that constructively interfere. So, and you can see why from this diagram too. Like it's not possible for arrival in this correlation to be slower than the arrivals that are exactly in line. So it's not possible for there to be a slower arrival. So that's the only place where you don't get destructive interference. In all the other areas, the waves destructively interfere. So from this kind of principle, you can see that you correlate and extract enough noise, and if you've got good conditions, then you can extract what's called the Green's function, or the virtual source signal between station pairs. What's also interesting about this figure is you can see that there is some extraneous information here too. So the signal that propagates from southwest to northeast is exactly the time reverse from the one that goes from the northeast and southwest. So we're measuring the same path twice, which is of course redundant. So it should be reciprocal, so we should have the same information. So what that implies is we only really need one-sided illumination. So only from 180 degrees, we need noise coming from one direction. Then we can at least one of the two station pairs, we can construct this virtual source signal. So we can do imaging with that. So once we have these signals, this kind of shows the kind of move-out plot that we typically see. So you can see we have noise coming from everywhere, and then for all station pairs here arranged by inter-station distance, we see this move-out, so the wave arriving at a certain time. Now this is for a homogeneous velocity, so for a constant velocity, so this forms a perfect V. But you'll see if we have again, here's the homogeneous velocity, but you can see if we have a heterogeneous velocity model, then you can see differences in the arrival times of these move-outs. You can still generally see this trend, this move-out trend, but we see that some of these station pairs sample predominantly the fast zones, so these have faster arrivals, and some preferentially sample the slower zones, and these are. So you can see basically from this is the kind of procedure of how we go from measuring correlation functions to getting a map of the velocities. So the basic idea is we construct the virtual source signals for station pairs, we filter them in frequency bands, and we pick the arrivals, and we invert those to produce a velocity map as a function of frequency. Just to kind of show you for different velocity models, we see obviously different move-out patterns. So this one is obviously considerably slower than this one, so you see that a lot of the arrivals are delayed. So if we repeat this for a bunch of different frequencies, so we do narrow bandpass filters around the correlation functions, and we repeat it for a bunch of frequencies, effectively what we then have is a velocity map as a function of frequency, or a velocity map for each cell in 2D space and for each frequency. So what you effectively have for each cell then is what's called a dispersion curve. For each cell, we have an idea of how the velocity varies as a function of frequency. So first we measured the velocities between station pairs, then we invert those to find the spatial distribution of the velocities for different frequencies, and then we have a dispersion curve. Now, once we have how the velocity varies as a function of frequency for each cell, we can invert those by using sensitivity kernels. So this is what we see on the right here. This shows the variation in Rayleigh wave speed as a function of variation of shear wave speed as a function of phase. So, for instance, what we see here for 5 Hz, we see that the sensitivity is peaked here around, say, 100 meters or 200 meter depth. which means that if we make a measurement at 5 hertz of the wave speeds, it approximately corresponds to variations at about 200 or 100 meter depth. And by repeating these again for different frequencies, we can invert to find the velocity as a function of depth instead of frequency. It's really just the mapping from velocity as a function of frequency to velocity as a function of depth. A few interesting things to note here, which will become important in my next section, is that we see that at high frequencies, these kernels are relatively peaked and relatively narrow. So like I mentioned, at 5 hertz, we can confidently assign a depth, or relatively confidently assign a depth to that. But if we look deeper at, say, 1 hertz or 0.7 hertz, we see that, yes, the sample is much deeper, but there's also, the peak itself is much broader as well. So when it comes to inverting these measurements, there is a lot more uncertainty the deeper we go because of the distributed net or the wide sensitivity kernels we have there. The figure here on the bottom right shows this procedure of inverting velocity as a function of frequency to velocity as a function of depth. So the Rayleigh wave phase velocities you typically measure are most sensitive to S wave velocity. So that's why you'll see most of the models we produce will be shear wave velocity. So here we can see this is a kind of a nice example because we can see this is calibrated to a borehole. So the layer depths here were known relatively well, and we can just invert for the velocity of each layer. Okay, so that was a very quick rundown of how the method works. I'm going to now discuss some of the limitations and some of the improvements we can make to the method, or where we can make improvements. The questions will be, under what circumstances can we use the method? What can and can't we image with the method? What kind of array spacings do we typically need to see what we want to see? What seismic instruments we'll need, which will then obviously lead into the node that we developed, and also how we can speed up the process. So the first thing that we need to deal with is when we are faced with a situation where we have imperfect noise. So as I mentioned, if we have 180-degree illumination or noise coming from any 180-degree angles, then we can make measurements from all station pairs. But if the noise is dominated by a single source that's relatively close by, then we can only use pairs that are relatively well aligned with these sources. So in this case, you can see any stations that are orientated in this north-northwest direction can be used, and even ones that are slightly off axis, because we can correct for the bias due to the incidence angles. But pairs that are orthogonal to this, we can't make measurements, because firstly, the uncertainty will be massive because the arrival times will be close to 0. And secondly, we can't even correct for the sensitivity kernels because they'll be like basically disparate. So the simplest thing to do is to adjust the array configuration based on the noise conditions. So in this case, you can see if we rotated this array by, say, 70 degrees clockwise, we would see that most of the station pairs would be well aligned to the source. And secondly, it would be also to move the array further away from the noise source. So the reason why moving the stations further away is beneficial as well is because these waves are scattered on the way towards the array. So the further you are away from this singular noise source, so say from a crusher, for instance, the more these waves are scattered and the more it kind of comes in as a plane wave as opposed to a single source. But in reality, the best way to deal with it is to kind of anticipate what the noise conditions will be or to measure it. So here's an example of a mining area in Arizona where there's clearly lots of mining and infrastructure going on. So if we deploy the array basically in this anywhere down this green area, we see we will have almost 180-degree illumination. So we can perform imaging without any reduced resolution whatsoever. Similarly, if we place the array right in the middle of these three, that would also be fine, or if we move further away from it. Also, there might be obviously noise sources here that are out of picture, so there might be things coming from the south as well. But the one thing we don't want to do is we don't want the array to be right over a mine. Now, this is in some cases unfortunate because obviously for brownfield exploration, we do want to look right over into the mine. And there are ways that we can deal with these cases, but it's really hard to deal with it if this is the dominant source of noise. So this situation would even be more favorable if this mine, for instance, was, well, it would have been fine if this mine is shut down, but if the other two mines were operating at full steam, then we would still probably be able to use this. But without knowing that information, we run the risk of this being the only noise source in the area, and obviously the process not working. Another example here is here we have an open pit mine in the northwest, we have a town to the east, and we've got a highway to the south. So in this case, really, you can deploy the array almost everywhere. You can deploy it in the middle, you see that's good illumination. You can deploy it there or to the northeast, and you would have really good noise conditions. But what we don't want, again, is having arrays right over the top of the noise source. So there's just no way for us to deal with that effectively. So you can imagine if you only work with pairs that are in line with the noise source and the noise is in the middle of the array, then it leaves a big blind spot exactly in the middle of the array. And it's like effectively only emit regularly out. The other limitation of the method is there are inherent uncertainties in the measurements. So effectively what we have is from a correlation function like the one in the top here. We can filter them in different frequency bands and measure the wave speed arrivals, but we have inherent sensitivity, uncertainty in these measurements that's based on the signal to noise ratio and the frequency. And a useful relationship to use here is called the Kramer-Rao lower bound. Typically, this is used if you've got two very similar signals. This tells you what is the lowest uncertainty you have in making measurements of the differences between the two signals. You can kind of flip the script a little bit, and you can say, if you have two very similar correlation functions, when is something in the detectable range and when is it within the uncertainty? I'll explain this a little bit. So here's an example. Here we have two ground profiles. So we've got three layers, and we have a dispersion curve on the left. So this is the data we measure, the dispersion curve. And you can see if we introduce a very thin layer at 400 meter depth, you can see the effect on the dispersion would be very small, and it will be within our uncertainty limits. Now this problem, you can see this is a travel time. So the further away the stations are, the smaller this uncertainty. And also the higher the noise ratio, or the higher the frequency, the lower the uncertainty. So the basic idea is if you have infinite signal to noise ratio, you can make measurements that are extremely 100% accurate. Or similarly, if you've got infinite frequency, then you're giving it the direct delta function and you can pick the arrival immediately. But in reality, we have some uncertainties. So I'm going to use this relationship to kind of discuss some of the questions we commonly get about where can the method be applied, and then use this relationship to kind of show some of the limitations. So this is again, sorry for my graphic cartoons, but this is say a setting where we've got, say, unconsolidated sediments that are about 50 meters. We've got sediments down to 500 meters, and then a crystalline basement below that. I'm going to discuss four kind of questions we get frequently. So one being detecting a thin layer within the sediments. Second being a vertical feature or something like a dike, a vertical intrusion in the model. The last being a dense body or a fast body or a slow body in the basement. And then finally also discuss variations in the basement topography or the basement depth. I'm going to show you which one of these are detectable and under what circumstances they are detectable. So let's start first. If we have a really thin layer in the sediments, so again, what we see here is not that clear from the figure, but we see in the background there's a black, which is our background model. Then we see the introduction of a very thin layer. It's only a 10 meter layer with 10% loss difference within the sediments. And we see in black the original dispersion curve, and in red the variation by introducing this new layer, and the dashed line, the uncertainty in our measurements due to this Kramer-Rao lower bound. So you can see if we only have a 10 meter thick layer at 100 meter depth, it's practically on our detection limit. We can't really see it. It's nearly in our uncertainty measurements. But if that layer is either faster, then you can see that there we start to see some separation between the two curves, and we can, in theory, detect that difference. Or if the layer is flatter or thicker, we can see the same thing. Now you can see in this case, this is a 10-meter layer, 100-meter depth. If we move it down to 200 meters, again, we can see that it disappears within our uncertainty bounds. On the other hand, if we make this 20 meters thick instead of 10, then again, it becomes detectable. So it's really an interplay between the thickness of the layer and the velocity contrast of the layer between those. In fact, it's a product of the thickness versus the contrast. Now, again, if this becomes really deep, so at 400-meter depth, we have difficulty seeing this effect. And from our perspective, from the measurements we make, these two cases look identical. Now, as I mentioned before, there's an interesting consequence. If the stations are far apart, you can see this is in theory detectable because the uncertainty of measurement is uncertainty in time, travel time. So the further away the stations, the less significant the travel time becomes. But the stations are closer together, we see that this uncertainty grows. The other thing that we know is that if we increase the SNR, the signal to noise ratio, then we can make more accurate measurements. And again, this becomes on the edge, but kind of detectable. So you can see whenever we get questions about can we detect the quartz layer in sediments or can we see a shale layer, then it's about knowing what do we imagine is the thickness of, what do you think is the thickness of the layer approximately, what is the velocity contrast, and then we can see is that even detectable with our method. Can we even with surface weight see that layer? And you can see it's under certain circumstances you can, and under others you can't. The second one we get frequently, and this is kind of reminiscent of the core lithium example where we saw that pegmatite dye, is if we've got a steeply dipping intrusion in the sediments. So in this case, for this core example, this is 50 meters wide and it's a velocity of 2,400 meters per second. Now the interesting part about this example, if you look at these two stations, the amount of time that wave actually samples that vertical feature is minuscule. So the stations are a kilometer apart, it only sees that 50-meter layer for a very small amount of time. So how you model that is you just take the percentage of the travel time or the path length effectively that it samples at medium, and you can see even though this is 2,400 meters per second, it only results in a layer that's effectively 30 meters per second faster for our path integrated measurement. So again, if your stations are a kilometer apart, you can barely see this. Like Adrian mentioned, if you're a kilometer apart, you can't see something that's 50 meters wide. And here you'd be tempted to see if you've got stations really close together. So if you've got stations that are 200 meters apart, what happens then? So two things happen. So first, you can see the velocity contrast becomes significant because the waves sample this dye for a quarter or 25% of the travel path. So the velocity contrast in that layer becomes significant. And you can see it then becomes quite detectable up to a certain point or a certain depth, if you want to look at it in frequency or depth. And here it's also conceivable for stations that are 200 meters apart, we can have a significantly higher signal to noise ratio. So if you have a signal to noise ratio of 30, so basically a big peak in the correlation functions, then we can detect this down to relatively deep depths. So you see here down to about 2 hertz becomes detectable. We can also kind of investigate this problem in another way. We can because this is a vertical feature, we can consider that at 5 hertz, effectively the model looks like a 2D model with just 2 velocity anomalies, or this is now with 2 dikes, but at 1 velocity anomaly. So what we can see here is again this velocity anomaly of this subvertical feature compared to a homogeneous background velocity. And on the right, we see the integrated path measurements. So you can see here, the lines here are colored by their effective velocity, or how fast it looks like they're traveling based on the arrival times. So even by eye, you can see in a zero noise simulation or infinite signal to noise ratio level, we can see these fast zones, and we can invert them to produce exactly where these high velocities are. You can see it's not perfect, and that's because of our limited ray distribution. But then you can see if we introduce uncertainty, uncertainty according to the Premier-Hour low bound I showed before, then it becomes just on the detectable limit. We can just see these, but we can also see noise elsewhere, so errors that are being fed. So yeah, so it's an example there. Basically, again, it depends on the thickness of the body you want to image, the velocity contrast, and basically the amount of time that you sample it. Here you can see array spacing is really important. With the stations that are kilometer apart, there's no way that we can see a thin vertical structure. But if we're close enough, or the stations are close enough, then you can see it. And in fact, what's happening on this figure on the right, for most of the long station pairs that interact with this fast zone, the measurements are, the difference in measurements are below our uncertainties. So basically, we don't make any significant measurements. And it's only the stations that are close by here surrounding this that can see it with any significance. Then another example is if we've got a dense, say a deposit in the basement, something like an ASEG. So here we kind of model something that's really fast, like 3,700 meters per second for BS, and it's 500 meters wide. So interestingly, you can see from the velocity profile perspective, it looks like it's quite a big change in the model, but because of the decrease or the smeared out sensitivity as a function of depth, we can see that it's only barely detectable. And you can see it's because of this large uncertainty at low frequencies. So you can see this, even though there's quite a big difference in these two dispersion curves, you see that at low frequencies that is quite within our uncertainties. So there are a couple of ways you can deal with this. And first, a few things to note here is, note the low frequencies when you consider here. We need to look like below 1 hertz. So in this case, if we want to use something like nodes that are using active seismic, we know that there's sensitivity, because they're 5 hertz geophones or 10 hertz geophones. We know their sensitivity is really low at 1 hertz. So we know the chances of getting a high signal to noise ratio there means you either have to record for a very long time, or you need to be very close to some really loud things. But if we could somehow manage to increase the signal to noise ratio to 20, then we can see we can detect this deposit down, basically down to a kilometer depth, down to as deep as we want. The final example is just a very simple one, is variations in the basement depth. And this is one's pretty intuitive. So if the basement depth is 20 meters shallower than it was before, so 480 versus 500, from our perspective, it looks almost the same. Like there's no change in the measurements. But if we look vary by 50 meters, then we can see it is detectable. So again, it's there are limits to the method. We can't. So what this means is we can't get like paleotopography at 500 meters with more than 20 meter accuracy. Our method just wouldn't allow it. We just don't have that sensitivity. But at 50 meters seems doable. It's achievable. So yeah, so a couple of things to note from these examples. Those of you who've been paying close attention would have noticed we look at much lower frequency than active seismic probe. We look really below 5 hertz. So that means that unfortunately, the nodal geophones that are using active seismic are not that useful, even though they're really like robust and low cost and easy to use. They're not the ideal instruments for this method. The other key takeaways are that we make path integrated measurements between station pairs. So it really depends on the size of the target and the velocity contrast of the target. And in fact, it's the product of the two. The smaller the body that we want to image, the more pronounced the velocity contrast needs to be for us to be able to see it, which is quite intuitive. And the station spacing relative to the lateral size of what we want to see is important. So if we have stations that are very far apart, they can't see thin bodies because the samples for such a small period of their travel times. Yeah, and the bigger, the higher the SNR that we have, the lower the uncertainty on measurements, the more detectable slight variations in geology become. So that leads kind of nicely into why we developed a node for ambient noise tomography. So So as I showed before, the kind of frequency response from the commercially available nodes aren't ideal. So this figure on the bottom right shows some popular nodes, so like NewSize, Geospace, Fairfield Nodal, and Smart Solo, and just the instrument response function. So that's just the sensitivity of the geophone as a function of frequency, and that's in volts per meter per second. So even though these are classified as high sensitivity geophones, they're about 80 volts per meter per second, and that obviously tapers down. So you can see at 1 hertz, they hover around, say, the 30 volts per meter per second. And so for the geode, we use the 2 hertz geophone element and a high sensitivity geophone element. So they're 260 volts per meter per second and a 2 hertz central frequency. So that means at 1 hertz again, or say at 1 hertz, when we were looking at say 30 volts per meter per second, we're now looking at something more like roughly 80. So the same sensitivity at 1 hertz as the others at the incumbents at 5 hertz. The other thing that we do is we use a lower sampling rate and a lower noise digitizer. We don't need to sample at 1,000 samples per second if we're looking at waves below 5 hertz. So we can use a lower noise and a lower sampling rate digitizer, and that just results in an instrument noise floor that's quite significantly lower than the incumbents. So what that means is if you're in really remote areas where the cultural noise functions are really low, it increases your probability of recording actual seismic noise and coherent seismic noise across the array. And it also means that you potentially increase your signal to noise ratio with the point time. So we did an experiment in South Australia, in a relatively remote part of South Australia. And we did 4 co-located geodes with 2 hertz elements and NewSize. So we used the highest pre-amplified gain and lowest sampling rates that the NewSize offer, which is 42 decibels and 250 hertz. And we compared what the correlation functions look like over time and also the total stack. So this image, for those who are familiar with it, shows the cross-correlation functions for short time intervals for 10 minutes. So for each 10 minutes, there's a line here that corresponds to correlation function, and in black shows the total stack. And with identical processing from A to Z, it shows the geodes. So there are definitely times where you can see that the correlation functions in the geodes are significantly stronger than the NewSize ones. And you can also see an overall larger signal to noise ratio in the correlation functions in the stack. And if you quantify those, you can see the effect is most pronounced at low frequencies. So below 0.5 hertz, you can see the geodes in about 4 days or 5 days reach something like 25 signal to noise ratio, which again gives us the possibility to detect really deep features compared to around 12 for the NewSize correlation. And we also see this is the same case for other frequency bands, with the higher frequency band showing the least improvement as we expect, because higher frequency band we get, the more equivalent the sensitivities are. Yeah, so the other thing about the geodes are they do collect data in real time. We process data and we analyze data in real time. And there are 2 main benefits to real-time data. So obviously you get results much faster, so you can get a 3D image in hours and not weeks. But you can also analyze noise conditions in real time. So instead of having blind nodes in the field where you harvest the data and then you realize the noise is coming from one direction, you can measure that in real time, and that enables the field crew to go adjust the array if it's not very well oriented towards the noise. This is an example in South Australia where we're about 40 kilometers northeast of Prominent Hill. So this is kind of a nice example where we see that, and this is a beamforming image, so we beamform the noise to see which direction it comes from. And you can see in this case, it's a nice example, even though it's a single mine that's the source, it becomes quite distributed by the time that it reaches our array, because it scatters on the way through to the array. So we can assess the conditions in real time, we can make adjustments to the array to be more favorable for the noise conditions if it's unfavorable. And the other aspect is to enable more dynamic imaging. So, for instance, those of you who've been to an ultrasound technician recently noticed how much they would move the ultrasound wand around to get a better view of the target. And we hope that with dynamic and real-time arrays, we would see something similar. We would see an array being put out, we could see an image in real time, and it would allow the field crew to kind of adjust the array based on certain noise conditions, but also on areas that look prospective and other areas that look barren. Yeah, so the process for us in developing a real-time node started in 2020, and it started, like I would say, with the JCAR version of a real-time node. And we moved in 2021 with something that worked really well, but it required a base station. So we transmitted data from the node to a base station over LoRa, the low power long range communication. The base station would then transmit data with high bandwidth, power to the cloud, something like Starlink or 3G. This worked really well, but firstly, like constructing this this base station was obviously added logistical overhead, which is unnecessary. And also in the areas where we had a lot of topography or topographic relief, it meant that in some cases we had to have one base station for every 3 stations. It kind of defeated the purpose in a lot of ways of what we were trying to achieve. And so we moved to the geode, which is direct to satellite node. So each geode has a satellite modem on top. It's a low power direct to satellite Internet of Things modem. So we do the pre-processing on the device, which really reduces the data rates. The data is then transmitted directly from the device anywhere on Earth to the cloud. So for those interested in more the technical details of the device, we just did publish a paper on it. So feel free to go look at that. Okay, so got a few minutes left, and my talk that promised something about the Moon and Mars as well. So I will shift focus now. So this is a photo that one of our founders always says inspired us to move in this industry, and this is Buzz Aldrin deploying a passive seismic sensor on the moon in 1969, so more than 50 years ago. And if you look at this device, it's really impressive. It's solar powered, low power, really sensitive. And it's really what we kind of strive to achieve with the geode in a sense, a really compact remote device. And if we look at how we, and some of I mentioned Fleet's ambitious goals is not to really even provide tools for exploring on Earth, but also to find resources on the Moon and Mars with geophysics. And this might sound a little bit outlandish, but I mean, we are a space company, so this is what we're going to do. And to kind of just point out the similarities, if we look at NASA's InSight mission, how we explore on Mars is by this the InSight lander, so it's sort of 2 seismic instruments, a short period and a long period high sensitivity device. It was followed by 2 CubeSats that's orbiting Mars, that's collecting data, just like what we do here. And we also recently obviously heard about Ingenuity, which is the first helicopter that landed on Mars in the first test flight. So at the moment, what the Ingenuity is kind of a nice change, and for us geophysicists, it kind of paves the way for potential airborne or small airborne surveys on Mars, which would be really fantastic. But otherwise, if we want to find any kind of resources with geophysics on Moon and Mars, we have to shift our thinking a little bit from big landers that are designed to give information about the deep crustal features of these planetary bodies. And we want to move more to distributed arrays like we do on Earth. So whether that would likely be seismic stations, magnetometers, and gravimeters, all in a very compact, low-power package. It would either be combined with a small rover that autonomously kind of roves and covers large ground that images areas as we go, or it would be via penetrators. So these are basically lawn darts that shot from orbits and then penetrate in the regolith. And of course, data would be collected by satellites. So we want to kind of collect data as satellites. So yeah, Fleet, as I mentioned, we've got some of these audacious goals, and on our current timeline or our thinking and how we want to achieve this is our first milestone is in 2025. We want to land a seismic station on the far side of the moon in the Schrodinger basin. So this is what's pictured here with gravity overlaying on top of it. So we've submitted several proposal to do this, and we're hoping to hear back about this soon. And the goal would be to use a commercial lander and have our device tethered to the lander and show that you can use very compact, relatively low-cost device to measure properties of the shallow lunar crust. The Schrödinger Basin is really interesting from that perspective because obviously it's a massive meteorite impact zone, and there's a lot of prospectivity for water ice in the shallow lunar crust there. Yeah, so the device, it's called SPIDER, so it's a seismic payload for interplanetary development for some kind of acronym. And the idea is that it will be tethered to a lunar lander, so a commercial lander, and would collect data on something like that. The next step would be towards the end of the decade to land something here, and this is in Kalgoorlie. This is in Mars. So we wanted to land devices on Mars. So again, it's hopefully distributed arrays, either tiny rovers or penetrators, and investigate some of the resource potential on Mars. So there's obviously lots of hints on Mars to the kind of things we're looking at Earth. So lots of meteorite impacts, volcanic features such as dikes are visible from the surface. There's large volcanic provinces there as well, similar to the ones we have on Earth that host lots of mineral deposits. Okay, so that's basically all I had to say tonight. So please feel free to ask any questions.
Fantastic. Thank you very much, Gerrit. That's really, really good talk. In a minute, I'll try and switch to see if there's any online questions as well. And I know there's going to be some questions in the room, but I just want to just quickly say first, there's a lot of talk at the moment about disruption in general, about technology and in our industry. And to me, this is one of those truly exciting things that I think can be disruptive. I was up at James Cook University last week, end of last week, for the 40th anniversary of the Economic Geology Research Unit up there. And one of the discussions we had was around how do we inspire the next generation to become geologists and geophysicists in an industry which is, you know, sometimes perceived as not being a sexy thing to get involved with. And seeing things like this is actually, you know, if this doesn't inspire people to get involved in geophysics, and I don't know what will. So I think it's fantastic what these guys are doing, and yeah, thank you again. We'll move on to some questions. So maybe while I check online, we'll start within the room with Hoya.
Please come to the microphone.
Sure, yeah, thanks.
Yeah, thank you very much for that nice talk. And you showed us a series of anomalous geological models reflecting to the dispersion curves, and some are separable, some are not separable, and those lines separable quite nice on the basis of the model. But when you collect seismic data and transform into frequency velocity domain, then very often, to my experience, it's the image is blurred and can need to be separable.
So the question was not really about can we, in theory, detect these geological anomalies, as you mentioned, but can you measure them? Because obviously we know like models and reality are different. So when you see a FTAN image, or when you see like we're trying to fit the Bessel function or whatever, however you measure your dispersion curves, then you're right, then there is a lot of noise, there's a lot of ringing, there's a lot of aliasing. So there's lots of tools and tricks involved in picking these curves. So yeah, so that is one of the challenges. But if you think about the uncertainty that I mentioned, that does try and incorporate basically the width of those peaks that you see. So for instance, if you see a FTAN dispersion image, it's obviously not just a beautiful peak that you pick, it's got some width to it. So as long as you can guide your picking enough to pick on the right branch, then these uncertainties should be valid. If you don't know anything about the subsurface and you're confronted with a dispersion curve, I agree with you, it's lots of times it's really challenging to know what's the fundamental mode, what's the first higher mode, what's the body weight contamination. And it comes, I guess, down to a lot of other problems where we do need to have a relatively good idea of, we have to have some idea of the subsurface. We do need some domain knowledge about the geology we're in and the properties. And from that, you can guide the rest. So you can clean up a dispersion curve a lot by kind of like cleaning or filtering it around expected geology, for instance. So yes, so that is a science in itself. We do also, of course, benefit from the reduction. So if we do make measurements on many different pairs, and as long as what we're looking at isn't very, very small, then we do get the square root n reduction of random noise through the disperse process. So yeah, but yes, that's a good point. It is challenging.
Thank you. Any more in the room? Yeah, go ahead.
I have a question about the type of noise you require. In particular, the body example, where we're looking at a body within the basement. Don't you require energy to come from below it, essentially, like so that's earthquake energy rather than man-made energy, which would come from the surface and maybe not pass through it. Is that right? Or?
Yeah, so I'll just repeat the question for online. So,
Yeah. Oh, sure.
yeah. So the question was, if we're trying to detect something, say at a kilometer depth, something in the basement, do we need energy coming from below to be able to image it, like an earthquake, or any seismic earthquake or anything like that? And the answer with this method is no. So we use surface waves and the dispersion of surface waves. So surface waves travel along the Earth's free surface, but the lower the frequency, the deeper they sample. So waves, say at 1 hertz, will sample down to a kilometer depth. But so basically, the sources can be distributed anywhere on the Earth's surface, and in fact, the surface waves attenuate much slower than body waves because they only travel along the free surface. So they attenuate like r squared instead of r cubed, which is like body waves that travel on a 3D body. But we do need relatively good illumination, and in that case, with these bodies, low frequencies.
Yeah. What's the main frequency that you usually get back to the general time of the Earth?
Yeah, so the question is about what kind of frequencies you record and what processes cause basically what frequencies. So the kind of general rule of thumb is below 1 hertz, we're looking at properties like the ocean interacting with the coast. So these can be really distant, but they attenuate really slowly. These low frequency waves attenuate really slowly, like bass and speed. At between 1 and 10 hertz, we typically look at other meteorological effects. So wind interacting with the crust. Lakes are a big source of noise. They've got their own microtide force lakes. And wind waves on lakes cause just that difference in the wave height causes pressure wave on the lake bed. And above 10 hertz, it's anthropogenic activity. So above 10 hertz, it's the crusher, it's the highway, it's water pumps, things like that.
Okay, so we've got an online question. So is there any work into looking at a combination of different geophysical methods into the real-time analysis of the seismics to add more information to the subsurface?
Okay, yeah, it's a great question. So yes, we absolutely are investigating, including other geophysical methods to improve the stability and the depth penetration and the resolution of the inversion. The obvious one for seismic is gravity. So typically, you can build an empirical relationship between velocity and density. So from measuring the gravity at surface, you can invert that together with the dispersion curve if you build this empirical relationship between velocity and density. There are a few published ones, like the Nafi-Drake curve, effectively, and Brochure's equation. But we do find, especially for mineralized rock, they often buck the trend. So for instance, nickel massive sulfides, even though they're really dense, are often slower than the volcanic host. So we often do have to either rely on some petrophysics on site or even try and make some measurements on core samples to build that empirical relationship. And then once we have that, yes, we can absolutely include gravity in the joint conversion. Other methods are trickier because it's not easy to say with magnetic susceptibility, for instance. There's not really an easy way to construct the relationship between that and seismic velocity. You can sometimes with something like conductivity do that because, say for instance, you have a porous granite, then you can kind of assign some resistivity values to that and assign velocities to porous granite, include something like that. But it's kind of hard to automate and do in real time because it's not really kind of artisanal.
Okay, well, I can't see. Let me just double check. Yeah. Okay, so we have one more question, I think. So truly fantastic stuff. Great to see progress in the hardware. How feasible are autonomous drones to speed node deployment and retrieval for spacings ranging up to hundreds of meters or more in difficult terrain? Are they light enough? I think that's a pretty big challenge, that one.
Yeah, so that's a great question. So obviously, because of our kind of space ambitions, we do want to make devices that can be deployed either by drone or by tiny rovers. And to do that, we do need to shrink down the devices. So, for instance, instead of using a geophone, we would use a MEMS. You can get really sensitive MEMS nowadays. And so that is something we're working towards. And I think that's something that naturally fits in with our company's profile of trying to develop technology to speed all those stuff. So yes, if you ever ask a question, that's absolutely in our technology roadmap. Yeah.
Good stuff. Well, I might. We're slightly over time, so I might, certainly for the online section, I might leave it there. Thank you to everyone for joining online. I do apologise for a little bit of background noise during the presentation. As I said, we're kind of trying new venues, and you know, you try and work with these things, but appreciate everyone joining. If there's any other questions, feel free to reach out to me or directly to Gerrit on LinkedIn. Yeah, thank you very much for joining. And if anybody around the Brisbane area, next time, please do join us in person. It's good to see some returning faces here, and I hope others will join in the future. So thank you very much.